Hello, welcome in the last lecture of my course Convection Heat Transfer. In this lecture we will be doing some sums, okay, and we will be targeting some sums in the domain of convection inside a pipeline, inside a duct, as well as we will try to see one sum related to mass transfer. Okay. So, first let me show you what are the problems we are having. So, first problem is like this. Let us say we are having water which is being heated in a 0.5 centimeter diameter tube. So, tube is having 0.5 centimeter diameter from 20 degree to 80 degree. A uniform flux of 0.6 watt per centimeter square is applied to the surface of the tube. Okay. So, that means you have a uniform heat flux case over here. Okay. The mean water velocity is 0.2 meter per second, and you have to neglect the entrance effect. So, thermal entrance region need not to be considered. You have to determine the maximum surface temperature of the tube. Okay. So, this is the problem we are having. So, this you can see this is nothing but actually pipe flow having constant applied surface heat flux. Okay. So, let us see how this problem can be solved over here. So, to solve this, to get the problem what we are having, we will be taking a schematic of the problem. Let us say this is the pipeline whatever we are having. So, let us say this is the pipeline whatever we are having, and we are having certain inflow having velocity, let us say u bar, okay, and the temperature of the inflow is, let us say, Tmi, and on the other hand side we are having the outflow, this is Tmo. Okay. So, inflow temperature and outflow temperature we have shown. Let us say throughout the pipe we are having constant heat flux. So, we are having constant heat flux like this. Okay. So, this heat flux let us say we consider that is Qs double dashed. Okay. So, this is the situation, we need to find out what is the temperature of the pipe wall. Okay. So, this is the problem we are having in our hand. So, to do that, first let me try to derive what is the wall temperature with respect to my pipe axial direction x. Okay, and let us say this is my radial direction y. So, in this case we can write down that Q amount of heat, let us say Q amount of heat is being supplied to the pipe wall. So, Q into perimeter of the pipe and length x. So, this is the total area through which the heat is being supplied. So, Q into P into x is equals to whatever amount, this amount of heat will be taken by the water inside. So, M into Cp into Tm of x. So, this is actually the mean temperature of the fluid, or you can say bulk temperature of the fluid. So, Tmx minus Tmi. Okay. So, in this inflow temperature. So, temperature of the fluid will be increasing by virtue of this heat addition. So, if you continue from here, we can write down Tmx is actually equals to Tmi plus Qp x by m into Cp. Okay. So, this we have seen. Okay. Now, if you try from the other hand, let us say we try to find out from heat transfer. So, Q will be actually heat transfer coefficient H. Let us say this H is obviously a function of x. So, let me write down Hx multiplied by your wall temperature. So, let us say Twx which will be also a function of x, Twx minus of Tmx, okay, because heat is being transferred from the wall to the fluid. Okay. So, this is from my heat transfer. So, if we add these two, so from here also we can see what is wall temperature. So, Twx is actually coming equals to Tmx and then plus Q by Hx. Q is a constant, so I am not taking that one as a function of x. So, this we have seen. Now, here we have already found out what is Tmx. If we put the Tmx from here to here, then I can get Twx is actually equal to, we can say Tmx will be replaced by Tmi plus Q Px by Mcp. Okay. So, this is actually Tmx plus Q by Hx. Okay. So, this we can write down. So, ultimately this Twx, let me write it over here, Twx can be written as Tmi plus, let me take Q common. So, it will be Q into Px. So, Px by Mcp plus 1 by Hx. Okay. So, this become my equation of the wall. Okay. So, we have to start with this one. In this problem you see we have to first see what is the perimeter and what is the M for this tube. So, let me do that one. So, let me do that one over here. So, if we do that part over here, then we can simplify this equation further. Let me show you how we can do that. So, we have seen this PLQ is actually equivalent to MCP and then TMO minus of TMI. Why I have written this? Because this is considering the whole pipeline. Let us say the pipe is having length L. Okay. So, for the whole pipeline, inlet temperature and exit temperature is coming over here and L is coming over here. P into L is the total area through which the heat flux is being applied. So, if you try to find out L from here, so L will become MCP and then TMO minus of TMI, okay, divided by P into Q. Okay, P into Q. So, if you try to put now the value of M and P in terms of the tube, so M will be pi by 4 into d square into your rho, and then for the axial direction we have to take U. Okay, and then this Cp Tm dot O minus Tmi will remain. Okay. And in the lower side P can be written as pi into d, which is nothing but perimeter for the tube, okay, and Q. Okay. After simplification this can be written as rho d u then Cp rho d u Cp Tmo minus Tmi, okay, divided by 4 into Q. D here will be cancelling out. So, we have found out rho into Q. So, we have found out this L over here. Okay. Now, you see, let us also try to find out the final expression for TW by putting the P and M in terms of tube. So, if you do so, so TW of X actually becomes Tw of x actually becomes Tmi plus Q we have taken common. I am writing this equation now. Q I have taken common, and then in case of P by MCP, P by M over here I have already written what is P, pi d, and M will be nothing but pi by 4 d square rho into U. If you put it over there, it will become 4L by rho d u Cp, okay, rho d u Cp and 1 by H L. Okay. So, 1 by H L. So, this is actually expression for TW at the end of the pipe. So, TWL, because I have put x equals to L over here. Okay. So, these two equations we have found out. So, next let us try to see that for this flow whatever we are having over here, what is the Reynolds number. To get the Reynolds number we have to get the properties. So, let me show you the properties. So, let me keep these two final form of the equation over here. Okay. So, this was L. So, properties if we try to see, now we have to find the properties. You see it was actually 20 degree to 80 degree. Okay. So, the properties we need to find at 60 degree. Okay. So, water at 60 degree mean temperature, water at 50 degree, 20 plus 80. So, water at 20 plus 80 by 2. So, that means is equals to 50 degree. Okay. So, in this we can get the properties as first let me see Cp, because that will be important. So, Cp will be 4182. So, this you can find out from any steam table. So, 4182 joule per kg Kelvin. Okay. Then we are having K, thermal conductivity K. So, that is actually it will be also coming from the steam table 0.6405 okay, watt per meter Kelvin. Okay. And then we are having Prandtl number. Prandtl number is actually 3.57 at 50 degree for water. Then we are having nu. Okay, nu will be also required 0.5537 into 10 to the power minus 6 okay, meter square per second. Okay, and then we are having rho. Density will be obviously required. This is 988 for water at 50 degree kg per meter cube. Okay. So, with all these properties we will try to first find out what is the Reynolds number. So, first let us see whether it is laminar or turbulent. So, if we try to see the Reynolds number becomes 0.2 into 0.005 okay, divided by 0.55 okay, 37 into 10 to the power minus 6. Okay. So, Reynolds number will come out as 1806. So, that means it is less than 2400. So, it is laminar. Okay. So, it is laminar. So, if it is laminar and we are having actually constant heat flux case for a pipe flow. So, we can use our Nusselt number correlation. So, let me see, this already I have told in the lectures. So, for constant heat flux laminar case, the Nusselt number will become 4.364 okay, 4.364. So, this Nusselt number can be written as Hx diameter of the tube by K. Okay, Hx diameter of the tube by K. So, Hx from here become 4.364 okay, into 0.6405 which is K divided by 0.005 which is the diameter. So, if you calculate, this comes out to be 559 watt per meter square Kelvin. Okay, watt per meter square Kelvin. Now, as we have obtained everything, let us try to first get the result of L. So, rho is known to me 988, D is known to me 0.005, U is given in the problem. So, U is actually 0.2 meter per second. Okay, Cp we have obtained for average temperature 4182, outlet and inlet temperatures are known as 20 degree and 80 degree respectively, and Q is constant. So, you can get the value of L because all the parameters are known. So, you will be getting this L comes out to be 10.33 meter. Okay, 10.33 meter. On the other hand, surface temperature TMI is known, Q is nothing but your 0.6 watt per centimeter square, and then your value of L is known. L is nothing but just now we have calculated 10.33 meter, and then rho, D, U, Cp all are known to you. HL just now we have found out over here. So, HL will be 559. So, if we put all this, so that means 20 plus 6000 multiplied by okay 4 into 10.33 which is L I have found out, then 988 is the density multiplied by 0.005 is the diameter. Okay, then multiplied by 0.2 is the velocity multiplied by Cp, Cp is 4182 and then plus 1 by H I have found out 559. So, if I put all these values, my TW at the end of the pipeline becomes something around 90.7 degree centigrade. Okay. So, in this problem we have found out these two answers. So, let me show you the correct answer over here. So, the correct answer will be 90.7. Okay. So, this is the first problem we have. Okay. Next, let me tell you what is the next problem we will be trying over here. So, next problem is air flows with a mean velocity of 2 meter per second through a tube diameter of 1 centimeter. The mean temperature at a given section in the fully developed region is 35 degree. So, here you see we are having constant wall temperature now. The surface of the tube is maintained at uniform temperature of 130 degree. So, surface temperature is 130 degree. You have to determine once again, just like the previous one, length of the tube section needed to raise the temperature to 105 degree. So, outlet temperature is 105 degree. So, it is just similar to previous one, only the difference is we are having uniform temperature. Okay. So, let me show you the problem over here once again. So, let me show you the problem over here once again. Now, this time we have to see air table because my working fluid is becoming air. So, let me show you with air this problem how it will be working. So, first just like the previous one, let me first derive what will be the wall temperature. So, MCP dTm, so change of the bulk temperature of the fluid is actually equivalent to Hx, heat transfer coefficient, then the temperature gradient obviously Tw minus Tmx, okay, at bulk temperature at location x multiplied by the area through which heat is coming. So, P is the perimeter, dx is the infinitesimal length. Okay. Now, if you do the integration both sides, then you will be getting ln of mean temperature at x minus of Tw surface temperature or wall temperature, you can say Tmi, okay, inlet temperature minus Tw is equals to minus P MCP 0 to x Hx dx, okay, Hx dx. Okay. So, after this if we proceed further and we consider that H is nothing but heat transfer coefficient is nothing but 1 by x 0 to x Hx dx. So, average heat transfer coefficient, if you write down like this, then this from here Tm can be written as mean temperature of the fluid, Tmx can be written as Tw, wall temperature is known to us for this case. So, Tw plus, and that is constant, Tw Tmi minus Tw into e to the power exp e to the power minus P average heat transfer coefficient, because this integration is becoming h bar, okay, P h bar by MCP into x. Okay. So, this is the equation we have got. Now, if you want to put x equals to L, then finally you get L is equals to MCP P h bar, okay, then ln of, now Tx will become actually Tw minus Tmi, okay. Now, Tx will become Tmo, okay. So, at the outlet the value becomes Tmo. So, this Tx actually became Tmo, okay. So, this equation we get for the L. So, now we need to just first ensure that whether the flow is laminar or not, and get the fluid property and find out the value of L. So, first let me tell you the fluid property. So, you see we are having temperature 35 degree and 105 degree. So, mean temperature is 35. So, Tm is actually 35 plus 105 divided by 2, that means 70 degree centigrade. So, at 70 degree centigrade for air we find out the properties, you can get it from air table. So, Cp is 1008.7 joule per kg Kelvin, okay. Your thermal conductivity K is 0.02922, okay, 0.02922 watt per meter Kelvin, okay. Prandtl number is actually 0.707, okay. Then nu is actually 19.9 into 10 to the power minus 6, okay, meter square per second, and rho will be also required 1.0287 kg per meter cube. Okay. So, with these properties, if you try to first find out what is Reynolds number, which is nothing but 2 into 0.01 divided by 0.01 divided by 19.9 into 10 to the power minus 6, this comes out to be 1005, which is nothing but laminar. Okay. So, this is laminar. So, once you get this is laminar, immediately you can understand what is the heat transfer coefficient becomes. So, heat transfer coefficient will be, Nusselt number will be, as it is constant temperature case, Nusselt number will be 3.657. So, this already we have discussed. So, Nusselt number becomes 3.657. Okay. So, if you write down Nusselt number in the form of H, then you will be getting H is nothing but 3.657 into 0.02922, this is nothing but the K. Okay. So, Nusselt number into K by D, which is nothing but 0.01 1 centimeter. Okay. So, here from we get the heat transfer coefficient is 10.69 watt per meter square Kelvin. So, now we have everything in this equation. H bar was required. So, this is H bar. So, H bar was required. Now, we can put everything over here. So, L is becoming now. So, let me write down L once again from here. So, L is nothing but pi into d square, d is nothing but 0.01 okay, square by 4 okay, by 4 into your rho is density for air is 1.0287 okay. Velocity is nothing but your 2 meter per second. So, it is 2. So, this becomes your m, and then Cp just now we have found out for mean temperature 1008.7 okay, divided by, first it will be coming perimeter, which is nothing but pi into d 0.01 into you are having H bar. Just now we have found out H bar as 10.69, and then we are having logarithmic over here. So, we are having logarithmic over here. So, logarithmic of Tw, which is nothing but 130 degree wall temperature minus of inlet temperature 35 degree divided by 130 degree minus 105 degree is the outlet temperature. So, 105 degree is the outlet temperature. So, this is 105 okay. So, if you calculate this L, this becomes 0.65 meter. So, this is my final answer okay. So, let me show you the final answer over here. So, this is my final answer 0.65 meter. Let me go to the next problem. So, next problem is related to mass transfer. Here I have shown the problem, a thin liquid film of ammonia which has formed on the inner surface of a tube of diameter d equals to 10 millimeter and length equals to 1 meter is removed by passing dry air through the tube at a flow rate of 3 into 10 to the power minus 4 kg per second. The tube and the air are at 25 degree centigrade. What is the average mass transfer coefficient? So, in this case you have to find out the mass transfer coefficient. So, this is a problem involving mass transfer. So, let me first show you the schematic of the problem, and then I will be going to the derivation of the solution. Okay. So, let me show you the schematic okay. So, it is a problem related to mass transfer which we have learnt in the 19th lecture. So, let me show you the schematic first. So, here we have the schematic. We are having a tube okay. We are having a tube where we are having ammonia film okay. So, this is let us say the ammonia film okay. This is let us say ammonia film. The tube is having diameter 10 millimeter okay, and tube is having temperature of 25 degree centigrade okay, and the length of the tube, that is also given, length of the tube is given as 1 meter okay, 1 meter. So, we are having ammonia film over here, ammonia film over here okay, ammonia film over here okay. And here is some airflow okay. So, airflow is having at a flow rate of m dot is 3 into 10 to the power minus 4 kg per second, okay, 3 into 10 to the power minus 4 kg per second, okay, and we have to actually find out, and temperature is inflow temperature is 25 degrees centigrade. Okay, so we have to find out what is the mass transfer coefficient Hm. Okay, so for this situation, if we try, so as air is at 25 degrees, so let us first find out what are the properties required, and at 25 degree what are the properties. So air at 25 degrees centigrade, air at 25 degrees centigrade. So first we require what is gamma, what is nu, nu is 15.7 kinematic viscosity into 10 to the power minus 6, okay, meter square per second. Then we require what is the viscosity mu, which is nothing but 183.6 into 10 to the power minus 7, okay, minus 7 Newton second per meter square. We require the diffusivity. So, this you can find from some property table of air at 50 degree, at 25 degree. So, this becomes 0.28 into 10 to the power minus 4 meter square per second. Unit of diffusivity is meter square per second, we have seen earlier. Smith number, so ultimately the Smith number will become nu by DAB. So, okay, so once we get nu and DAB, we can get the ratio of that. So, it becomes 0.56. Okay, this two ratio becomes 0.56, and if you calculate Reynolds number from here also, so Reynolds number is nothing but 4 m dot by pi d mu, okay, 4 m dot by pi d mu, okay. So, m dot is given. So, if we put the values over here, 4 into 3 into 10 to the power minus 4 divided by pi into 0.01 into mu is 183.6, okay, into 10 to the power minus 7, okay. So, if we put this, then Reynolds number becomes 2080, which is nothing but laminar zone, okay, less than 2400. So, this is laminar. So, we can use all the laminar equations. So, we know that we have already seen Sherwood number is important for mass transfer. So, Sherwood number becomes this formulation we have also shown, A into Re, okay, then Smith number by L by D to the power n, okay. Here we need to find out the value of A and value of n, okay. Now, let me tell you, for this type of pipe flow cases, this I have not told you in the lectures. So, A will be coming out as 1.86 and n will be nothing but 1 by 3, okay. So, if you apply this, then we can find out for the Sherwood number, this becomes 1.86 into, okay, so 2080. Smith number we have found out as 0.56 over here, 0.56 over here, 0.56 over here. L by D, L is actually 1 meter, L is 1 meter, okay. So, 1 by D, D is 10 millimeter, which is nothing but 0.01 meter, okay, to the power 1/3, okay. So, if you calculate this, so Sherwood number becomes 4.22, okay. Now, this Sherwood number will be helping me to find out the mass transfer coefficient. So, mass transfer coefficient Hm, this we have discussed in lecture, is equals to Sherwood number DAB by the tube diameter, okay. So, it is analogous to Nusselt number. Nusselt number is HD by K, Sherwood number is HMD by DAB, okay. So, from here, as we have also obtained the value of DAB from the property table, which is nothing but 0.28 into 10 to the power minus 4, we can get it is nothing but 4.22, Sherwood number is 4.22, okay, into 0.28 into 10 to the power minus 4 divided by D, diameter of the tube is 0.01. So, my mass transfer coefficient comes out to be 0.012 meter per second, okay, 0.012 meter per second. So, this is the final answer we are having for this problem. Let me show you the answer over here. This is 0.012 meter per second as we have obtained, okay. So, this is a very nice example of mass transfer question. Please keep on practice sums like this, and all the best for the exam. Thank you.